Jester. We've got everything set up. I had a tech come in and help me with. Yeah. Looks like none of the committee members are here though. We're gonna have something for you.
You're right. So next time, we can do it on this week. I'm like this.
What should I do? Oh, okay. Hey, Jeff, are you able to hear me?
Yes.
Okay, cool.
I'm breaking up the. Oh, Raphael is online.
Yeah.
Yeah, hi Raphael.
Hey, how are you?
Good. Yeah. Okay, we can hear you. That's great. Yeah, maybe we can send a quick email to the rest of the committee.
I'm just gonna follow up. I tried to remind him a couple of days ago. Okay. Oh, join it too.
Hi, guys.
Hi. Yeah. Okay.
Hello,
Hi, Raphael. Nice to see you.
good to see you again. Yes.
Yeah.
So are you going to use the board at all?
Probably not.
Okay, no, that's great. Then we'll summarize the point today.
Maybe you said this already. Are you going to share the screen with the slides?
Yeah, I wanted to make sure everyone is first.
Okay, awesome.
Oh, I think we're waiting on Matt Baker and Bruce Barron. So
Yes. Open it and I can start Matt. They try to find it on the Zoom.
we have another committee member.
Oh, nice. Okay. That's very almost.
Oh, okay. Almost ready to start.
Oh, okay. Oh, let's wait for Matt to come back.
Yeah, are you all able to see the slides on the Zoom presentation?
I can see them very well. Yes.
Okay.
I guess she find it. There, yeah. All right, yeah. So we get started. Yeah, thanks for all for coming to Maxie Defense, especially the committee members. So the plan is that Maxie is going to talk for about 45 minutes, Yeah.
Give or take, yeah.
give or take, say 40 to 50 minutes, and then anybody is welcome to ask questions, and then committee will ask questions, and then next will be asked if all the committee discuss, and then we will invite you back.
Okay.
Like that. And then we have some forms that will deal with. All right, yeah, please.
Okay. So the title of my thesis is Factorization Theorems and Canonical Representations for Generating Functions of Special Sums. I'm Maxie Schmidt. Okay, so as Josephine was saying, we have 5 committee members, all of which are here today. And thank you for joining on Zoom. Okay, so let's just go ahead and get started with the presentation. So I have an overview of topics. So what I'm going to first do is give a general introduction to sequence generating functions, which I'm going to abbreviate as OGFs. We're going to motivate certain quote factorized forms of OGS for special sums, and we'll see what I mean by that in a few slides. I'm going to give a few examples and main results from the publications that are covered in my thesis. And then I'm going to explore some topics on the frontier research of this research area. And then at the end, we're also going to have questions from the committee and the audience. Okay. First thing I want to do is basically introduce what an ordinary generating function is for a sequence. So given a sequence, so f of n from n greater than or equal to 0, so just f0, f1, and so on, we define its ordinary generating function, or OGF, to be this function. So f of z is going to be the sum n greater than or equal to 0, f of n times z of n. And z is just basically some variable that we use to define the power series. We're going to use the following notation, which is for n greater than or equal to 0, this bracket z of n of the generating function f of z is going to be equal to the coefficient f of n. It's just coefficient extraction. That's fairly common notation. So when we start thinking about what a sequence generating function is, so a good concise explanation that I'm a fan of is going to be found in Wilf's book, Generating Functionology. So a generating function is a closed line in which we hang out the sequence of numbers for display. So we can treat f of z using complex analysis, or we can work with it formally. So you don't necessarily need to treat it as any z for any particular value where it would converge necessarily, although you can if you like. Usually we only consider integer sequences or sometimes rational ones by taking f of n over n factorial. And that's usually called the EGF, or the exponential generating function of a sequence. Okay. So the focus of my thesis is on several peer-reviewed publications that I've gotten into print from 2017 to 2021. So in other words, since enrolling at Georgia Tech. Primary publications that are summarized in the thesis are given by these reference numbers, and I have the bibliography at the end of the slides. So it's basically going to be focused on these ones. Other related publications on so-called Jacobi type generating functions, or J fractions, are also found in the references, and it's going to be given by these numbers. And then some other peer-reviewed publications over this time period can be found in these references. Okay, so again, these first ones are going to be basically what's summarized in the thesis. Okay, so we want to look at some motivation for the ordinary generating function of some special sum. So we're going to look at these so-called Lambert series generating function cases, so LGFs. So we need some notation here. For arithmetic functions f and g, we define their Dirichlet convolution at n by this notation. So f star g at n is going to be the sum of over the divisors of n, d dividing n, f of d, and then times g at n over d. And this is for any integer n greater than or equal to 1. A Lambert series generating function, which we're going to abbreviate LGF, is an OGF, or ordinary generating function, for a sequence that allows us to generate multiplicative functions, which are expressed via divisor sums of the form f, and then convolved with just the unit function 1. So we define this L sub f of q to be the Lambert series generating function of f. It's going to be the sum n greater than or equal to 1 f of n times q to the n over 1 minus q to the n. And when you expand this out in terms of powers of q, what you get on the right-hand side here is going to be the sum. It's actually the sum n greater than or equal to 1, the sums f convolved with 1 at m, and then times q to the m. So you can basically see, or you can prove fairly easily, that the Lambert series generating functions are related to the ordinary generating function of the sequence by noting that f of q, which is the sequence's, just f of n's ordinary generating function, is going to be the Lambert series generating function of f convolved with the Mobius function at q, where mu of n is, of course, the Mobius function. Okay. So some examples of LGFs, some number theoretic LGFs where this type of series comes up. You can take the Lambert series generating function of the Mobius function, and what you get by a known identity of mu convolved with 1, you're just going to get the variable q back. You can look at Euler's Toshin function, and the Lambert series generating function of Euler's Toshin function is going to be given by this. So you can see that phi convolved with 1 is going to give you n for all n greater than or equal to 1. So it gives you this power series, which in this case, we actually need to restrict convergence of q. So usually we would just treat q formally, but here we're just going to define that q has to be less than 1 in modulus. Okay, we can look at some, for alpha in the reals, we can look at n to the alpha, the Lambert series generating function of this, and what you get is the generalized sum of divisors function out of it on this side. So you see that n to the alpha convolved with 1 is going to give you the sum of divisors relation on the right-hand side. We can look at the Lambda function, and what we get is that the special generating function here, when you get this, you get the sum of n greater than or equal to 1, q to the m squared, which can sometimes be related to theta functions. And then the capital lambda function of n, or what you get when you take the capital lambda function, involve it with 1, you get log of n at each n greater than or equal to 1. So these are just some examples of places where these generating functions come up. Okay, so before we really get into the results that started to motivate this type of expansion, I want to cover some basic notation. So we can use Iverson's notation to express basically compactly, like set things to 0 and 1 in some convenient manner. So the symbol pond, and I'm going to use like in brackets, and then with little delta, is going to be 0 or 1 valued, and it's going to be 1 if and only if the condition con is true. And this is fairly standard in some books, like Concrete Math book, for example. We use this notation for the greatest common divisor, or the GCD of n and m. So you can write GCD out this way, or we can just drop the GCD and just use parentheses this way. So NM is the GCD of n and m. We're also going to need something called the infinite Q polymer symbol. So for parameters a and q, sometimes we can set a equal to q. It's going to be a q sub infinity is going to be equal to this infinite product. So it's the product of m greater than or equal to 1, 1 minus a q to the m minus 1. And usually we don't look at conversions, but you can set modulus of q to be less than 1 if you need to. And then we look at some people call this Euler's partition function. Mercer-Merca is actually fond of calling this Euler's partition function, but the partition function is the number of unordered partitions of n. We denote this by p of n. It's also equal to this coefficient of this generating function. So it's coefficient of q to the n and the series expansion of the reciprocal of the infinite Q polymer symbol QQ infinity. Okay. So we're also going to need these sequences, which are restricted partition functions. So the sequence is S of E of nk and respectively S of O of nk, or the number of k's in all partitions of n into an even and respectively odd number of distinct parts. And we usually define these just for k less than or equal to n. So n is greater than or equal to 1 and k is in the range of 1 to n. Okay. All right, so that's just notation. So factorization theorems, and where this term factorization theorem actually came up, is going to be found in some overlapping publications that I worked on and that I had in common with Mercer-Merca. So around 2016, I had an article published in Acta Arithmetica, and Mercer-Merca had similarly explored some similar ideas, and we got together and decided to start generalizing these. So these are the references for the first two, 17 and 3. Co-authored work with him over the next few years found in these references. So the key idea, or the motivating idea here, is to rewrite the LGF series. So this L sub f of q as in the following, the left-hand side expansion. So we have the Lambert series here of f, and we're going to write this as in this factorized form. So 1 over the infinite Q polymer symbol times the sum n greater than or equal to 1, and then at each n we're going to sum from k equals 1 to n. We're going to define these lower triangular matrices S sub nk, and then weight it by f of k in the sum, and then of course q to the n just to complete the series expansion. So we're going to refer to this equation again, it's LGF-ft, so for factorization theorem. For any n greater than or equal to 1, the matrices, so you basically truncate the matrix at n, and you form an invertible lower triangular sequence. So they're lower triangular with ones on the diagonal, and hence they're invertible. Okay, so we proved this, and I'm not going to go into the details of the proof here, but just it's good to know. So what Mercer-Merca was able to show was that S of nk is equal to S of O nk minus S of E nk, these difference of restricted partition functions. And then we got together and we proved that the inverse of this matrix is actually given at nk. So for k greater than equal to n, for k greater than n, it's going to be 0 value because it's also similarly lower triangular. But when k is in the range of 1 up to n, it's given by this divisor sum. So the sum d divided by n, p of d minus k, so this k is fixed here, the partition function, and then times the Mobius function mu at n over d. So some interpretations of these results, these matrices. So if we go back to this, what we mean by factorization theorem is you're basically writing this as a factorization. So an OGF here, in this case, we have it defined in this fixed OGF, and then times a matrix. So it's basically written as a matrix factorization of the generating function on the left-hand side. Okay, so interpretations, what this gave was some interesting new ties between the OGFs for multiplicative functions. So these functions where you can generate f star 1 in the series expansion, and the more additive theory of partitions. So this is noted to be sort of an unusual connection. So something that I've looked at since these publications came up were the following key questions. So why was the factor, the reciprocal factor of QQ infinity in the OGF factorization, this LGF FT, which we tagged, so natural? So why was it that you got this, extracted this new, interesting new information out of it? So that is these ties between multiplicative functions and the theory of partitions. So in one sense, just for the special case, collecting common denominators of the partial sums of these on the right-hand side, so these f of n times q to the n over 1 minus q to the n. If you collect common denominators, you get this OGF factor in the limiting case. So this is sort of an algebraic rationale in this particular sum type for why that was the most natural. And the question to keep in mind for later is there a deeper underlying principle to explain why this factorized form was the most natural way to write this type of expansion and why we got some interesting new ideas out of it. Okay. Okay, so I had quite a few results to pick out. I just wanted to give a couple of ideas of some of the other results aside from just the fact that you can write these factorizations this way. So this is one of my favorites. This one was actually proved in the Acta Arithmetic article, which was the motivation for getting together with Marissa Merca and co-authoring a bunch of papers later. So the normalized average order of the function f is going to be defined by the following. So we're going to use this notation capital sigma sub f of x is defined equal to the sum n less than or equal to x. So that's n from 1 up to x of f of n for x greater than or equal to 1. And then we're going to use this notation. So we're going to use the notation from the original article, which is a sub f of n is going to be equal to the sum k equals 1 up to n, s of nk, those same matrices that we defined that were the difference for the restricted partition functions, times f of k. Okay, so we have this theorem. So we have this theorem. So immediately it seems a little bit like, I guess, hard to parse, but let's just look at what it is. The summatory function of f convolved with 1 at n plus 1 is going to be equal to the sum. So b is just going to be in the range of plus or minus 1, and it's just a convenient way of writing pentagonal numbers out. It's going to be sum k up to this, which depends on b, negative 1 to the k plus 1 times the summatory function n plus 1 minus the pentagonal number here, so k times 3k plus b over 2. And then we get this sum right here, which is going to be the sum k equals 1 to n of a sub f k plus 1. So it gives you sort of a natural recursion for these summatory functions that depends on the pentagonal number. So there's some similar known expansions of the summatory or some recurrence relations for the summatory function of the sum of divisors function. So I'm going to cover that as a special case in the next slide. Okay, so this is just notation. So we use sigma n, which is the same thing as sigma 1 of n, which we've seen in the LGF examples before. It's just the sum of over the divisors d dividing n of d. So this is just what we're going to call the ordinary sum of divisors function. When you basically weight this by d to the alpha, you get sigma sum alpha, but here you were just going to set alpha equal to 1. So this is fairly standard notation. So we have this corollary of the result on the previous slide, which is that the summatory function of the sigma function, so the sum of divisors function at x plus 1, is going to be equal to this. So we use the sum here. We're changing from b equals plus or minus 1 to s plus or minus 1. So we sum from n equals 0 up to x. And then we have another inner sum here, k equals 1 up to this, square the square root of 24n plus 25 minus s over 6. And then we get this. So basically you have basically the pentagonal numbers here, and then you weight by the partition function p of n, or p of x minus n. So I haven't actually worked out the asymptotics of this, but I think it's actually kind of interesting. There are some definite asymptotic expansions for the partition function, which might be useful here. We can compare to classical bounds, the things you might see in Hardy and Wright, for example. You know that the summatory function of sigma of x is going to be pi squared over 12 times x squared, and that's going to be the main term of it, and then plus something that basically vanishes compared to the main term. There was an improvement due to Wallfish, and I believe it was in 1964, which is that you can write the main term here, and you can improve the error term to this. But this is basically the recurrence relation we get, and as it turns out, it's actually going to be explicit functions here. It's less of a recurrence relation. Okay, so take a drink of water. Wait. Okay. So branching out from LGFs. So what happens when we want to basically start looking at the OGFs, or the ordinary generating functions of sums that aren't just divisor sums? So things like the Lambert series case gave us divisor sums as the coefficient. So f convolved with 1 and m was the right-hand side of the LGF expansion. So we want to look at some motivation. So let's take, for example, let's decompose the average order sums, or the normalized average order sums. So sigma sub f of x So you can basically sum this up. So recall this was basically going to be the sum of n less than or equal to x of f of d, but you can break it into these cases. So the divisors of x, where d is going to be greater than 1. You can do the d in the range 1 to x, such that d and x have GCD 1. And then you can basically do the other terms, which is from d in the range from 2 up to x, such that the GCD of d and x is going to be somewhere in between. So not precisely 1, and then also not a divisor. So the first summations, as we've noticed before, were generated by the LGFs. So you can basically take these. So the sum d dividing x, d greater than 1, is going to be the coefficient of q to the n, and the series expansion of L sub f of q, and then we subtract out that term, just f of 1. It's just like a formality. So what about the next two sum terms? We wanted to see what we can do to generate these sort of special sums. Okay, so generalized factorization theorems for these type of sums, these GCD type sums, are found in 8. So this is a co-authored work I did with Hamid Musabe in around 2017. We got it published in the Ramanujan Journal in 2020. So for integers k in the range 1 up to x, we can define the following type 1 and type 2 sums. So we can define t sub f of x is going to be the sum d less than or d from 1 up to x, such that d and x have GCD of 1, f of d. And this can be kind of convenient. You can see things like the Euler's-Toshin function can fall out of this definition if you set f identically equal to 1, for example. So it's fairly natural. And then we can also define these type 2 sums. So for any f and g, fixed arithmetic functions, and then parameter k, and then at x, we're going to sum over the divisors of d of the GCD of k and x, and then we're going to have the sum ends are going to be f of d and then g of x over d. So special cases of this might be Ramanujan sums, for example. So the factorization theorems we considered in this paper are going to be now of the following form. So we can basically generate these t sub f of x's as the coefficient of q to the x in this series expansion. So we get a different set of lower triangular, invertible lower triangular matrices, t sub nk, and then we expand them similarly to how we did before in the LGF case. And then we can also take a different sort of way to look at this, and we can take the function g of x, and we can get it out of a series expansion of the following type. So you weight by reciprocal of the Q-Ponckheimer symbol, and then we take the sum n greater than or equal to 2, and then we sum k equals 1 up to n. We get these coefficients, these matrix coefficients, and then we basically weight by sums of this. Here we define this w to be a non-zero indeterminate parameter, which is inserted to enforce invertibility of the sequences use of nk. So you run into trouble with invertibility if you don't do that, which is why we looked in this sort of curious way. So I'm not going to cover very much in the paper, very much the rest of the results in the paper. There's some interesting stuff in there. But I just wanted to sort of give the flavor of this and look forward to generalizations of this type of idea of factorizations for more general special sums. Okay, so let's just look at some additional examples. So what other types of sums might we want to generate with generating functions of this type? So let's look at this example. So these A set convolutions. So for an integer n greater than or equal to 1, let A sub n be a subset of the divisors of n. We say that n is a primitive if an is equal to 1 in n. And then we define the set of a primitive positive integers by this. So this script mathcal a is defined equal to n greater than or equal to 1 in if n is a primitive, which is dependent on these sets a that we defined. And the reason we look at this is because if you define this way, sums of the next two types actually have a natural Mobius inversion type theorem associated with them. But we might choose to look at sums that look like this. So S of 1 of A of f and g of n is going to be this type of convolution. So it's going to be the sum divisors d dividing n restricted to the condition that d is in this set A, f of d and then g of n over d. And then we might also do something sort of similar, which is that we do the divisor sum d dividing n, except that we require that d in both n over d are in A. So we can look at sums like this. So that's just another example of the type of sums we might want to consider from this generating function, this factorization theorem type idea. So another example would be something called unitary convolutions. So we say that the unitary convolution of f and g at the integer n greater than or equal to 1 is defined by the following notation. So f convolved with g of n is going to be equal to the divisor sum, so the sum of divisors d dividing n, such that both d and n over d are equal, have GCD 1. they have no common factors. F of D and then G of N over D. That's another sum type we might be interested in generating with this type of expansion. And then I'm going to look at the third case, which is very generalized, and it sort of has some hefty notation involved in it, but it actually turns out to be kind of an interesting way to look at this. So these D kernel convolutions. So suppose that D, so we're just looking at a lower triangular an invertible function. So basically think of these as matrices, like if you form a truncated matrix. So so D maps from the positive integers onto some complex value, typically integers. We require that D of nk is 0 when k is greater than or equal to n. So that's going to enforce the lower triangular part of this, and that D at nn is not going to be 0, so that you basically get an invertible matrix out of it. We want to study a generalized class of deconvolution type sums of the following form. So we're going to write the convolution with respect to this kernel D, F convolved with G at n is going to be this sum. So you take the sum, so instead of summing over the divisors, for example, you're basically going to weight according to this kernel function. So k equals 1 up to n, f of k, and then g at n plus 1 minus k, and then times this kernel function weight for integers n greater than or equal to 1. So this is actually something that we look at more carefully in the more expository section, last section of my thesis. So keep this one in mind for what we're going to consider next. Okay, so definitions of generalized factorization type theorems of the form that we've seen in the LGF case and that we looked at in the generalized form with the co-authored work by myself and Musabe. Option 1. So we have something that looks like this. For n greater than or equal to 1 and a multiplier OGF CQ such that C of 0 is not equal to 0, we can look at sums of this type. So you sum over some set A of n, and then you weight whether whether you multiply by f of k. So these are basically 0. Think of these as 0 and 1 value matrices. So something important here is we would get an expansion that looks like this. So instead of the infinite q polymer symbol, we're going to replace it by just this arbitrary generating function C of q, subject to the fact that C of 0 is not equal to 0. And we get something like this. So for each fixed set A, and then for each fixed generating function C, we get a set of invertible lower triangular matrices B sub nk, and then the dependence on A and C is here. And then we form a similar type sum here. So it's the sum in greater than or equal to 1. I'm basically collapsing the inner sum here. And then we also take the sum from k equals 1 up to n. And then these matrices weight by f of k, and then you have the q of n here. There's another option for doing this, which is that we don't have just 0, 1 valued weights like we did in the divisor sum cases. So the LGF cases that we've seen so far in option 1. We define weight functions, so some script t sub nk. So we might want to look at sums of this type. So think of this like t and k were like a binomial coefficient or a Stirling number or something like that. You can form sums that look like this. So sum k equals 1 up to n, this weight function, and then times f of k is going to be equal to a similar, the coefficient of q to the n in a similar factorized type expansion. So again, for each fixed set of coefficients t and each fixed OGFC, you're going to get this lower triangular matrix definition here. Okay, so these generalized sums allow us to consider weighted forms of the special cases that we saw in the LGF and the GCD type sum factorizations. Okay, so is this fairly clear with the order of the quantifiers that you? Okay, so yeah, so something like this would be the generalization of that. So we want to go back to the question that I had posed earlier. Which is a good open question to ask from the LGF case. So let's recall this. The original factorization theorem expansion for the LGF case are of this form. So we had that we wrote the Lambert series generating function of f of q is going to be equal to 1 over the infinite q Pochhammer symbol, and then times this sum, where these are invertible lower triangular coefficients. So we proved that the ordinary matrix entries S sub nk, oh, that's a typo, is going to be the difference of these restricted partition functions. We also proved that the inverse is tied to partition functions by showing that it's sum over the divisors d of n, the partition function d minus k, and then times the Mobius function at n over d. So in both of these cases, we get the matrix entries and the inverses in the expansion. We get the factorization theorem here is expressed in terms of partition theoretic functions. So this gave, as we pointed out before, new connections between functions in multiplicative number theory and the theory of partitions. So we want to look at this idea of defining like a canonically best OGF factorization. So in the view of taking the OGF CQ equals the q Pochhammer symbol, the infinite q Pochhammer symbol in the LGF case is going to be taken in some ways it's a qualitatively optimal or somehow encoding the most meaningful hidden information about this sum type. So the question is, how can we precisely define a corresponding quantitative metric to express that initial qualitative intuition for this special case, and then generalize it to more general sum types? So how do we get that type of relationship that we saw that was special in the LGF case more generally when you're looking at other sum types and you're looking to basically find this optimal CQ that expresses most information that would be found in the factorization theorem. Okay, so this is an idea. This is basically a first approximation. So you can take basically two n vectors, just in general. So the vector A is going to be the tuple A up to A of n, and then B similar. One standard way to evaluate how well matched these vectors are is going to be given by the normalized correlation statistic that we're going to call P-core for Pearson correlation, which is defined this way. So it's 1 over n, and then the sum j less or equal to n, the product of these two, and then basically sort of a variance, a normalizing variance sum, square root of it. And you can see that this statistic for any vectors A and B is always going to be in the range -1 to 1. So the idea, which is sort of a refinement of this idea, is to use the correlation statistic, which we tagged here, this PC stat, with the infinite sequences in place of n vectors. So we're going to look at basically infinite sums of things that look like this P-core of A and B. So what we want to do is basically find a way to express that these sequences, the correlation statistics should somehow depend on key features of the series coefficients of the generating function we choose CQ here and its reciprocal, and then also the kernel function d sub nk and its inverse. So we give some precise definitions in the thesis manuscript, but for now I just want to focus on to give some intuition on the special case. Okay, so I want to look at how to visualize what we're talking about doing here. So the high-level procedure. Let's say that we have just any OGF C of Q, which we're going to define to have C of 0 as 1, and then this is the notation for the series coefficients of this C of Q is C sub n, and then depending on the script C. We're also going to use some notation here for the set of unsigned pentagonal numbers, which are defined as follows. So the set of pentagonal numbers is going to be the sum j, or the set for j greater than or equal to 1, this g of j, which is defined as this. This is Mercer-Merca's way of expanding out pentagonal numbers. So you can see that you get out of this set 0, 1, 2, 5, 7, 12, 15, 22, and so on. Okay, so when we look at the LGF case, what we get is that the inverse matrix, of course, because we're looking at divisor sums, is going to be the Mobius function. So we're going to basically take the absolute value of it. So we're going to define for h, n, and k, f of LGF of C, which depends on this. Here C is going to be this infinite Q-Pochhammer symbol. But more generally, looking forward, it's going to be 1 over n. It's going to be if k is in the set in pentagonal, it's going to be 0, or it's going to be 1, and then we weight by the inverse function squared, the kernel inverse function squared, and then we have this term that pops out of the bottom. So we have 1 to the omega of n, and then times this sum. Okay, so this is again, this is a special case. We'll give the more general formula for the correlation statistics we look at in a couple of slides. But the idea for visualizing this is as follows. So we've formed the correlation matrix, which in the special case was given by this formula here. For the LGF case, that's what pops out. And we're just going to form for truncated n. In the next images I give, I think I took n out to 48, which is sufficient to sort of see the difference. You pick a clear target image. So here it's going to be the Linux penguin, which is going to be shown below, and partition its pixels into an n by n, capital N by n grid. You can involve the n size pixels with the respective correlation matrix, which should depend on C, but here we fix C to be the infinite Q-Pochhammer symbol. Or wait, hold on. Okay, I found a typo here. Okay, so this is actually okay. I apologize. This should be the C sub little k of script C, and it should depend on C here. When you take C is equal to the infinite Q-Pochhammer symbol, this is what you get. But in general, this should depend on C of the generating function C of Q that you use. Similarly here, it should be the square of it. Okay, so I apologize for that. But basically, what the idea is to visualize this, you're going to convolve the original image with this correlation matrix. And you should observe the following qualitative trends. So less distortion in the resulting image. So i.e. the clearer the results are when you convolve the original image with the correlation matrix should indicate good or high correlation. And more distortion, so blurrier results indicate poor or lower quality correlation. So I did some examples, some numerical examples, which are featured in the thesis. So this is our original image. So it's basically the Linux penguin here with some background. When you do this procedure with Mathematica and capital N is taken as 48, you get that basically there's a little bit of blurriness. So this is supposed to be our qualitatively optimal example. So you don't get that much distortion in this. If you take C of Q instead to be the inverse or the reciprocal of the Q Pochhammer symbol, you get a little bit more blurriness. You take just sort of another version of this, which is sort of somewhat arbitrary, but also gets to the point that that C of QQ should be the optimal generating function. You get even further blurrier results when you take the convolution. C of Q is equal to this generating function. Similarly, you get blurry results, and just C of Q is basically going to generate all ones. You similarly get this. So in some senses, this correlation statistic that we defined is going to capture what we wanted to see, which is to see that this is the qualitative best choice of CQ. So this is just a way of visualizing what we're after for generalized sum types. And this was again in the LGF case only. Okay, so based on inspection, the visual tux examples for the LGF case seem to conform to the ideal case expectation. That is, we cannot really do better than C of Q as we had defined to be qualitatively optimal. We found these interesting partition theoretic connections with multiplicative functions here, and we wanted to sort of replicate that for the more general cases. So for more general convolution sum types, we want to maximize or minimize. So basically find the maximal or minimal correlation of the following series. So core, so you're going to have a fixed kernel type D, and then you're going to basically be optimizing over all C. So you sum n greater than or equal to 1, and then you get something that looks like this. So in the LGF case, we found that this sum is going to be equal to the omega function. And here we're basically going to get something similar here. And we're going to take the absolute value just to basically keep it a little bit clean. And we basically want to do something very similar. So if you define a fixed sum type that you're interested in studying from this perspective, by these kernel functions d sub nk, you basically want to find that generating function CQ that basically gives the optimal amount of information out of it. So it's not clear how to do this. So even if we restrict this to integer coefficients and define that C of 0 is equal to 1, so basically so that you don't have that extra multiplier function hanging out there, this is very much an open topic. So some preliminary conjectures and discussion are given in the last section of my thesis. Some historical notes on where correlation statistic type tactics and correlation statistics are used to study number theoretic objects can be found in the survey article 9. Basically, Montgomery would have used pair correlation to study the non-trivial zeros of the zeta function. Later, Hagel, Rudnick, Sarnak, and Odlyzko respectively built on Montgomery's work to apply statistical analysis in the form of correlation statistics to L functions, the GUE, and in applications to random matrix theory. So this motivates that this type of perspective has definitely been looked at and successful in studying number theoretic objects in the past. Okay, okay, that's all I have now. Spare a few slides that I had. I think we're good for time though, so I don't need to get to those. So does anyone have questions for me, or just me?
Yeah. Yeah.
Sorry?
So you want to show us the remaining slides, right?
I just had some extra slides that are sort of
Okay. Well, that's awesome.
like filler material.
Yeah. Anybody has any questions? Because I have to see something.
I'm sorry, I'm a little bit nervous.
Yeah, that's okay. You spoke very fast. Yeah. Maybe if there's no question, maybe we can proceed by asking the.
Well, I'm going to ask a question.
Oh, okay, great. Yeah.
Okay.
You were saying that you thought the Q Pochhammer expansion was optimal, the inverse of the partition.
Yes. In the LGF case, yeah, for the sums that are generated by the LGFs.
Do you have some results quantifying that? I mean, it's very pretty.
I've looked at it, but this was basically, it was just basically a visualization, sort of a heuristic idea. I mean, qualitatively, that's what we want and expect. Like you get that in the limiting cases when you combine common denominators. So that's what we would expect. And then somehow we want to capture that idea that you actually do recover the optimal correlation statistic when you choose that. That's the idea. And then defining it that way. So these examples are suggestive of the fact that the way we're defining these correlation statistics is a good way to go. That captures that ideal case.
Can you, just to go back to really at the beginning, you had you had two partition statistics, even and odd. I just can't. Couldn't remember the definition exactly.
Is it here?
And into an even. The number of Ks, I see. Okay.
Yeah.
Yeah, I was done.
So these have nice like partition theoretic generating functions. They're restricted partition functions.
I'm having this case. So in these partitions, only 1K per partition, either 0 or 1K in each partition.
No, you basically look at the partitions of n into an even or odd number of partitions. You form those known partitions, and then you look at the number of Ks in each of those partitions and count them up.
Then what do you mean by distinct?
It was the number of distinct parts that was confusing me. Do the partitions have distinct parts, or can the parts be repeated?
I guess they have to have distinct parts. Yes, this would be like the Q partition function variant of it, and then you count the number of Ks in all those partitions. So an even number of distinct parts or an odd number of distinct parts, and then you look at the number of Ks in those partitions as a result.
Okay, thanks.
So the partitions don't have to have distinct parts, but you're just counting, like it matters to even or odd.
No, they do have that distinct parts. So the number you look at the okay, so let's just look at S of E of NK. So you take all the partitions of n into an even number of distinct parts. You look at those partitions, and then you count the number of Ks in those partitions.
The number of times K is appear.
Across all of the partitions.
Yes.
One time, right? As Jeff.
Sorry?
K can only appear either 0 or 1 time. Because the parts have to be.
The parts are distinct. That's why.
Yeah.
What you mean. I think what we're trying to figure out is, what do you mean by distinct parts? Maybe go with an example.
Okay.
Take a small n and small k.
Okay, sure. Let me move the camera over. Okay.
Yeah, that's good. That's good. The board is pretty centered. Thank you.
Okay, so we're looking at, let's just say, that's P of NK. So let's pick like n is equal to pi, right?
Yeah.
Let's pick K.
You could write a little bit lower. I mean, I think it's in the edge of the
Oh, yeah.
on the camera. Sorry.
Yeah, no worries. And the other thing is maybe, I don't know if you want to stop sharing
Yeah, that's
screen
fine.
right now.
Perfect.
Yeah.
No, sorry. Yeah, that's also a better solution. Move the camera a little bit. Thank you. Thank you. Thank you. Thank you. Thank you. Perfect.
Is that good? Okay, and then stop sharing. Okay. Okay, are you all able to see my screen still?
Yeah,
Yes,
great.
It's fantastic.
Nothing like a numerical example.
Okay.
Yes.
Okay, so let's look at the number of partitions and not necessarily making. Okay, so number of partitions. Okay, so we have one example. Two plus 2 plus 1. Five is 5 is 5, so then this would be 2 plus 3. So from these partitions, we're looking at the number of the distinct parts. Go to like that, because of the parts like that. Okay, so all we have here is distinct parts. Is this. Okay, so instead of just k equals 1, we can choose k. We're in the range of 5. So k equals 1. We have 0. K equals 2. Count the number of 2s and the number of partitions that satisfy this formula. We're going to get 1. K equals 3. So we're going to get 1. K equals 4, we get 0. K equals 5. Oh, we also no, wait, should have been 7 here. So I'm just trying to generate the right partition. So we have 4 plus 3, yeah. Should be 7, which means we'll this is good. So we have 4 plus 1. Yeah, okay, so 2 to 5 is 7. That was total. And then we're going to count the number of 1s in these. So I guess we actually here have this partition case 1. The number of 2s, we have just the 1, 2 here. 1. So k equals 3, 0, we get 1, 4, we get 1, k equals 5, we get 1. Okay, so that's going to be but it was an even number. Sorry, I'm a little flustered. Okay, so we have to, if we're going to look at S of B, we have to basically apply this one. So S of B, sorry, so K of 5 is okay, you guys can check it out. But the idea is basically to look at all these partitions, count the number of K's, and they satisfy the number of distinct parts, and then count the number of K's. So all that. Choose the 3s, 4s. If you were to look at S of O, so the number of odd parts, you basically like these. This gets rid of that one. 5. It's going to be on phosphorus 5. Yes. Okay. So something that might someone who likes to look at generating functions a little bit more carefully, or like first view of the generating function. Also see that S and K, which is going to be the difference of S and minus S O K. You can write it in terms of so it's going to be equal to the coefficient of give the K minus K. So that should be this side here. Okay, you guys good?
Yeah, is that okay? Yeah, I don't know if they can hear it. I don't know.
Oh, I stepped away from the microphone.
Yeah.
Sorry, I stepped away from the microphone. Was that fairly clear? At the end, I gave a formula for the difference that was basically in terms of the generating function for it. But basically, you look at the different partitions. You make sure that they're into a number of distinct parts. Then you look at either the even or odd number of components in the partition, and then you count the number of K's in there. That was what we were doing. So S of E is up there with the tabulations we did. Okay, does that answer the question?
Yeah.
Okay.
We probably go back to those text pictures for a bit.
Yeah. Okay, I'm gonna screen share again. Okay.
Yeah, looking at those pictures, C looks pretty good to me too. And then somehow like the only one where like, because the other one looks like the picture got shifted to the right and down.
Yeah, it's a variant of the Q hammer symbol. I just wanted to show that the QQ inputs are actually.
So for C, can you remind us what is the vectorization look like? Instead of the essence scale?
Okay, I don't think I actually I didn't define that precisely. So let me go back here. Go back to the board. The question is, what does the corresponding factorization theorem look
Yeah.
like when it's in terms of an arbitrary generating function C as opposed to the Q Pochhammer symbol we found in the LGF extension? So, yeah, it looks something like this. We want to write the LGF, which we have for a fixed function f, I'll let Q. So the coefficient of QDN, which we know is going to be 2f(1)(n). We're going to write it as this. So the coefficient of QDN 1 over this curly Q. We want to write factorization of this, which we think coefficient, series coefficient of QDN 1 over Q, so as opposed to what we saw that special case. And very one. Lower triangular invertible matrices, let's just call them S and K, and then they're going to depend on this Q, or sorry, this C. So like that, and it's here, and then that with K. So it should look something like that. And then when C is equal to C Q is equal to the property of C. And so then K is the same thing. Let's just keep that same base. It's that's the sum that we do.
That's right, yeah. So if you put in the inverse, then I formula that.
I mean, I suppose it boils down to like, would you choose to basically factorize it in terms of reciprocal or not? When you're doing this, it turns out thinking reciprocal and it gives you the nice partition theoretic connections.
Yeah.
I mean, it is still related to the algebraic case you get when you basically combine the common denominators. So maybe it's not unexpected that it's organized, it's still a little earlier than the original, but I don't really have to tweak the intuition on what to expect. I mean, what you get here is if you have Euler's prefigural number theorems, so like this QQ, then you have this expansion. It's 1 plus the sum invariant of 1. Negative 1 and use n. So 1, 2, 2, 1, but it's going to change. I mean, I guess it's going to change the statistics a little bit. That you're looking with, like the one I saw over here, which is actually the special case. Yeah, so something like this, it would change it a little bit. So as opposed to that partition function here, and you would be like this partition functions here, as opposed to it. I really haven't.
Okay, yeah. Any other questions? So I think it's online, either Jeff or Tom, you got questions.
No more questions.
Okay, yeah, thank you. So can we ask the general audience to leave and the community can stay for more questions?
The only thing is that this is actually being recorded. So if you don't want me to have a copy of this, let me just stop the recording.
Oh, it's up to you.